Ever just stop and wonder how we know all the stuff we know? The medicine we take, the phone in your hand? It all comes from science. But how does it really work? And maybe more importantly, why should we trust it? Let's get into it.
I mean, that's a huge question, right? We're constantly asked to trust what scientists say about, well, everything. But here's the thing. That trust isn't supposed to be blind. It's actually built on a very specific system. It's kind of like a promise.
And this promise of doing work with integrity, with respect, with real responsibility, that's the invisible foundation that holds up the entire scientific world.
And that foundation? It has a name: research ethics. And let me be clear, this is not just a friendly suggestion. These are the guiding principles every single credible scientist has to live by.
Think of it like the official rulebook for science. It's what makes sure the data is real, the methods are solid, and the conclusions are honest. It's the whole reason we could feel confident that a study's results are legit. But what happens when somebody just decides to tear a page out of that rulebook?
And when that promise breaks, the damage, well, it can be absolutely catastrophic. We're not just talking about one bad study. We're talking about a crack in our collective trust in science itself.
Okay, so this is where we meet the villain of our story: research misconduct. This is a deliberate, calculated betrayal of that foundational promise we talked about, and it shows up in a few different, nasty forms.
First, you've got plagiarism. That's pretty straightforward. It's just stealing someone else's work. Then there's fabrication, which is literally just making up data from thin air. Manipulation is a little sneakier. That's when you twist or alter real data to fit the story you want to tell. And finally, there's withholding, conveniently hiding the results that don't support your theory. Each one is just a different flavor of breaking that core promise of integrity. And this isn't some abstract academic problem. When ethics get thrown out the window, the consequences are very, very real, and they can be measured in human lives.
Just look at the infamous Paolo Macchiari case. Here you had a surgeon using a totally unproven experimental procedure on real patients, and the results were devastating. It was this brutal, tragic reminder that research misconduct isn't a victimless crime. It destroys careers, it costs lives, and it just shatters public trust.
It's a pretty scary problem, right? But here's the good news. Science has a hero in its corner. It has a powerful, rigorous process that's specifically designed to hunt down and eliminate error, bias, and even outright fraud. It's called the experimental method.
And this is the toolkit scientists use to find reliable answers. It's a structured way of asking questions that really is designed to prevent us from fooling ourselves. And it all starts with two key pieces.
So in any good experiment, you're always changing one thing on purpose. That's your independent variable. And you do that to see if it causes an effect on another thing, which you measure. The thing you measure, that's the dependent variable. It sounds simple, but making sure the results are actually reliable, that's where the real genius comes in.
So, how do you make an experiment rock solid? Well, first, you need a large sample size, lots of people or subjects, to make sure your results aren't just some random fluke. Second, you have to control every other variable you can think of, keeping them all constant. That way, you know it was your independent variable that actually caused the change. And finally, you absolutely need a control group, a group that gets no treatment at all to give you a baseline to compare against.
But here's where it gets really interesting, especially with that control group. Scientists have to deal with something called the placebo effect. Our minds are so powerful that just believing a treatment will work can cause real physical changes in our bodies. So how on earth do you test a new pill when a simple sugar pill can make people feel better too? Well, you fight fire with fire. In what's called a single-blind study, the patients have no idea if they're getting the real medicine or the placebo. But the gold standard, the best of the best, is a double-blind study. That's where neither the patient nor the researcher handing out the pills knows who is getting what. This removes bias from pretty much every angle, and it's the most powerful tool we have for getting a clear, unbiased result. Okay, so you did it. You ran a perfect, double-blind, controlled experiment. You've got your data. The hard part's over, right? Well, not quite. Now comes what might be the single biggest, most common trap in all of science.
I want you to burn these 4 words into your brain, because they are one of the most important critical thinking tools you will ever have. Correlation is not causation. Let me show you exactly what that means.
Okay, check out this chart. In the summer, as ice cream sales shoot up, the number of sunburn cases also shoots up. It's a perfect correlation, right? The two things move together, so you might be tempted to draw a conclusion.
Of course not, right? It sounds completely absurd. But the data shows a clear connection, a correlation. This is the trap. Just because two things happen in lockstep doesn't mean one is causing the other. So what is really going on here?
And there it is, the hidden factor. In this case, it's hot weather. The hot weather makes more people buy ice cream, and it makes more people go outside and get sunburned. The ice cream and the sunburns are correlated, for sure, but neither one is causing the other. A third factor is causing them both.
So this is the crucial difference to understand. Correlation is just noticing that two things seem to move together. It's a connection. But causation, that means you've proven that one thing directly makes the other thing happen. And believe me, that is a much, much higher bar to clear.
So let's wrap this all up. What's the big takeaway? Science is all about building confidence. A result that supports your idea makes it stronger, but it never proves it with 100% certainty. There's always more to learn. In fact, a scientific idea is only useful if it's falsifiable, meaning there has to be a way to prove it wrong, because it only takes one solid, contradictory result to show a hypothesis is false. And above all else, please always remember, a connection does not automatically mean causation. Seriously, think about it. The more you start looking for those hidden third factors, the more you'll start to see the world around you with the sharp, critical eyes of a scientist. And trust me, that is a superpower worth having.